Hello everyone, I'm Alka Jangir from IIT Kanpur, and this is your course Nature and Properties of Materials, offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. Now, this week's lectures included non-mechanical properties and laboratory demonstration. Now, firstly, we'll be going through some sample assignment questions, then we'll be going through some lecture slides. So, your first question is, which one of the following properties do not belong to diamagnetic materials? So, your first option is no magnetic dipoles in the absence of a magnetic field, or magnetic susceptibility is positive, or dipole moments are aligned opposite to external field direction, or magnetism arises only when an external field is applied. Your answer will be B. Now we can explain this by saying that in case of magnetic materials which align against the magnetic field, they are diamagnetic materials. Now magnetic susceptibility will be lesser than 0, which means it is always a negative value for diamagnetic materials. Now these materials are repelled by the magnets and move from a stronger to weaker field. These materials are independent of temperature, and these materials magnetize in the opposite direction. They do have a small amount of magnetization intensity. And examples are gold, tin, mercury, water, etc. are examples of diamagnetic materials, and diamagnetic materials have a constant relative permeability. Now, question number 2. So, the ratio of intensity of magnetization to the magnetization force is known as. Your options are flux density, susceptibility, relative permeability, or none of the above. Answer will be susceptibility. So we can explain this by saying that the ratio of magnetization to applied magnetizing field intensity is magnetic susceptibility. So this is your magnetization divided by field intensity. So this is dimensionless quantity, and these are the symbols and what they mean. Now moving to the question number 3, which of the following is expected to have a maximum permeability? Your options are brass, copper, zinc, and ebonite. The answer will be ebonite, and we can explain this by saying that the magnetic permeability of a material is its ability to acquire magnetism when it is exposed to a magnetic field, and it is the maximum for ferromagnetic materials. Now brass here is a diamagnetic nature, and brass is also an alloy of copper and zinc, and they both are also diamagnetic. So this nature is also attributed to its component metals, and the magnetic permeability of diamagnetic materials is less than the permeability of vacuum. And ebonite is paramagnetic material, so it has highest permeability among these options. Question number 4. Now, which one of the following materials is considered as a non-magnetic material? Your options are diamagnetic material, ferromagnetic material, ferrimagnetic material, or antiferrimagnetic material. Answer will be A, diamagnetic material. Now we can explain this by saying that a magnetic field repels diamagnetic materials because it induces a magnetic field that is directed in the opposing direction from that which is applied and producing a repelling force. So in case of diamagnetic material, as it is showing here, So here when we are applying no magnetic field, these diamagnetic moments, they are not aligned, but when we apply magnetic field, it aligns itself in opposing direction. Now diamagnetic substances are those substances which in their normal states have a magnetic moment, no magnetic moment at all, and the magnetic permeability of diamagnetic materials is less than the permeability of vacuum. Examples are bismuth, copper, gold, mercury, water, alcohol and hydrogen. Now these are different. In case of paramagnetic materials, when we apply this field, these will be aligned in the direction of applied field. And in case of ferrimagnetic and ferromagnetic, without application of magnetic field, there will be some kind of alignment before as well, and when we apply, it will be aligned as well. Now question number 5. Now question number 5 is, for transmitting the electrical energy over a long distance, the general preferred material is. Options are copper, steel reinforced aluminium, aluminium reinforced copper, aluminium reinforced silver wire. Answer will be silver reinforced aluminium. Now explanation. Transmission line cables have been made of aluminium since late 1800s, and there are many types of cables like AAC, ACSR and AAAC. Now among these, ACSR has been standard for long runs. It stands for aluminium core steel reinforced. So typical, and this is here steel reinforced aluminium, so this one is used. Now typically copper is only used for underground high voltage lines because its resistance is lower and it creates less heat, and it is harder to dissipate heat in an underground cable. Now for the question number 6, a material has refractive index of 2.5 if the light is falling normal from a glass sheet of refractive index 1.5, what will be the approximate reflectivity of the material? Your options are 0.512, 0.0625 or 0.256 or 0.0456. Answer will be B. Now we can explain this by, firstly, it is a simple formula for if the light is normal or perpendicular to the interface, then this is the formula that is given for reflectivity of material. So reflectivity will be N2 minus N1 divided by N2 plus N1 and whole square. Now N1 and N2 are the refractive indexes of two different sources that are there, okay, mediums through which light is going. So here N2 is 2.5, N1 is 1.5. So we'll be putting its value. 2.5 minus 1.5 will be 1 and 2.5 plus 1.5 will be 4. So its whole square, 1 by 4 whole square will be 0.0625. Now question number 7. In order to increase the electrical conductivity of a metal, the preferred method is increase the vibration level, decrease the temperature, increase the temperature or decrease the vibration level. So we know for the metals, as we decrease the temperature, its conductivity increases, and with decreasing temperature also vibration levels they reduces. But what we can control? We can control temperature. So answer will be decrease the temperature. Now in case of the electric conductivity of metals, it decreases with increase in temperature. It is due to an increase in the collision between free electrons, thereby increasing resistance. and it is reverse for the semiconductors, for which conductivity increases with temperatures, because in case of semiconductors more these uh, electrons, they become free to move, and that's why in case of semiconductors conductivity will increase with increasing temperature increases. In case of metals, here it is shown as we are increasing temperature, this resistivity it is increasing, so it is lowest at lower temperatures. So these are metals: copper, aluminium, iron, and here copper is highly conductive compared to iron and aluminium. Question number 8. Question number 8. Find the effect which is not related to the light absorption mechanism. The options are Tyndall effect, Compton scattering effect, photoelectric effect, Peltier effect. So the answer will be Peltier effect. Now all these effects are explained here. So for in case of Peltier effect, when an electric current is passed across a junction between two materials, then a temperature difference is created. One junction becomes cooler and one junction becomes hotter, and this effect is known as Peltier effect, named after the scientist who discovered it. Now this effect is not related to light absorption. Other effect is Tyndall effect, the light scattering by particles in a colloidal or in a very fine suspension. So this is related to this effect. In case of Compton scattering, the scattering of a high frequency photon after an interaction with a charged particle, usually an electron. And photoelectric effect is the emission of electrons when electromagnetic radiation such as light hits a material. So all these three effects are related to light absorption. Question number 9. So it is a numerical. So in this, light travels from air into an optical fiber with an index of refraction of 1.44. Then in which direction does the light bend if the angle of incidence of the fiber is 22 degree? What is the angle of refraction inside the fiber? So the options are it bends towards the normal and 15 degree. Option B is it bends towards the normal and 25 degree, or it bends away from the normal and 15 degree, or it bends away from the normal and 25 degree. So answer is A, and here it is solved. So we can see that this is how your this is how it will look like. So if this is the inside optical fiber and it is this light is traveling from air into optical fiber, so it is, if we consider it air and this one optical fiber, then it will hit at particular angle. So this angle is given 22 degree, and then at what angle we have to find out. It will pass inside this optical fiber, and refractive index n1 and n2 are given. N1 will be, for air we can easily search it online, or we can remember that it is 1.003, and for optical fiber it is given 1.44, and angle 22 is given. So by using Snell's law, which is n1 sine theta 1 equal to n2 sine theta 2, so we'll be putting all the values and we can easily calculate theta 2 value. So sine theta 2 will be 1.003 divided by 1.44 times 0.3746. Now theta 2 will be sine inverse 0.2602, and which will be 15.08. Now this angle will be with the normal. So it will be bends towards the normal and 15 degree. This will be correct answer. Question number 10. So the highest value of thermal conductivity is expected for, your options are steam, solid ice, melting ice and water. So we know thermal conductivity depends on mainly electron and your phonon. So these two combined, they are responsible for thermal conductivity. So it will be higher in case of solid objects. So solid ice will be your answer. Now since solids have a systematic organization of atoms and greater intermolecular forces than liquids do, so solid ice has higher thermal conductivity than melting ice, water and steam. Thermal conductivity is obtained by lattice vibrations, and thermal conductivity in solids is attributed to migration of free electrons and lattice vibrations. Therefore, thermal conductivity of a solid is the sum of electronic component and lattice vibration component. So these are the free electrons and these are the bonds which are lattice vibrations. Along these there will be transfer of heat. So this is the solid structure. So this will give you highest thermal conductivity. Now we'll be going through some lecture slides. So firstly, optical properties. So as the name of the lecture was, non-mechanical properties. So these first properties, optical properties. In it, firstly we'll be looking at electromagnetic spectrum. So this is the spectrum. This is the wavelength. So wavelength is increasing in lower direction, and as frequency is increasing in opposite direction, and as frequency increases, energy also increases. So this is the increasing photon energy. So firstly, highest wavelength is of radio waves, then microwaves. It is smaller for microwaves, then infrared, then visible light. This is very small spectrum. This only we can see, this part of the electromagnetic radiation. Then there is ultraviolet radiation, then there is X-rays, then there is gamma rays. So gamma rays have the highest energy and lowest this wavelength and highest frequency. Now this is the color and energy. So for various colors that we see, violet has 3.17 electron volt and red has 1.62, and others are 2.73, 2.52, 2.15 and 2.08. So red has the lowest energy. Now electromagnetic radiation. Each electromagnetic radiation is characterized by a combination of time varying electric field and a time varying magnetic field. So E and H, it will be propagating through space. This one is H and this one is E. So this is electric field. These are at 90 degree to each other, and the direction of both of these propagating, this will be direction of your movement of radiation. Now it has a specific range of wavelengths. All electromagnetic radiation traverses in the vacuum at a same velocity, which is 3 times 10 to the power 8 meter per second. Now these are the formulas that you should remember. Energy E is equal to S times nu, or H equal to C upon lambda. Here C is equal to 1 upon under root epsilon 0 mu 0. Now epsilon 0 is electric permittivity of vacuum, and mu naught is magnetic permittivity of vacuum, H is Planck's constant, and nu is frequency, which is in hertz or per second, lambda is wavelength in meter, c is velocity in meter per second. Light interactions with solids. So incident light is reflected, absorbed, scattered and transmitted. So here if a light ray is going on some object, so some part of it will be reflected. Depending on what is the properties of this material, some part of this ray will be absorbed, which is shown here, and some part of it will be transmitted through this. It is IT. So these are the intensities of light. So firstly, which is coming, it is part of the transmitted, absorbed and reflected. These all three combined. Now optical classification of materials. So materials can be of three types. It can be the transparent, it can be translucent, or it can be opaque. So example will be for transparent. If there is a single crystal, it is more likely to be transparent because grain boundaries and the defects that are present in other materials, they don't let this ray to go through this material. It will get scattered if there is presence of grain boundaries. Other material is polycrystalline dense. So if a material is dense but it is polycrystalline, it will be somewhat translucent. So some light can go through it but not all. Some will get scattered inside. Opaque will be polycrystalline porous. So porosity, if it is present inside, so it will make your material opaque. Optical properties of metals. So all frequencies of visible light are absorbed by metals because of the continuously available empty electron states which permit electron transitions. The incident radiation having frequencies within the visible range, they excite electrons into unoccupied energy states. Above the Fermi energy, this is Fermi energy level, above this, these electrons will get excited, and so the incident radiation is absorbed, hence metals are opaque. The Fermi energy is the maximum energy occupied by an electron at 0 Kelvin. The change in energy of the electron delta E is equal to the energy of the photon. Re-emission of a photon. So when these electrons will get excited, then these electrons will come back to its ground state, then it will emit some radiation. So the change in energy of the electron is equal to energy of photon, and the re-emission of photon of light takes place by a direct transition of an electron from high to low energy state. Metals are opaque to low frequency radiation. So if radio waves are coming onto a metal, then it will act as opaque. So radio waves to about some middle of ultraviolet rays. And metals are transparent to high frequencies such as X-rays and gamma rays. Now applications of optical phenomena. So these are some applications. First is luminescence. So it is the process where a material absorbs energy and then immediately emits visible radiation. It consists of electron excitation and then dropping down to lower energy states. So it will be re-emitting these absorbed energy. Now if the emission of radiation occurs within 10 to the power minus 8 seconds after excitation, then it is called luminescence. Otherwise, this type of luminescence is called fluorescence. And if it takes longer than this time, then it is known as phosphorescence. So ordinarily pure materials do not display the phenomena, but some special materials called phosphors have this capacity, such as barium, magnesium, aluminium 10, oxygen 70, this compound, and Y2O3, zinc sulfide and cadmium sulfide. Applications of these properties in making fluorescent lamps, CRT, cathode ray tube, plasma, video display screens, and white LEDs. Now, other phenomena is photoconductivity. So, in this, bombardment of semiconductors by photons with energy equal to or greater than the band gap may result in the creation of electron hole pairs that can be used to generate current, and this process is called photoconductivity, and it is different from photoelectric current in the sense that an electron hole pair is generated, while in case of photoelectric, there will be, when we are providing it electricity, the free electron cloud which is there in metals, only that will be moving around in the material. So that's why it is different. In here, electron hole pair will be generated. And in this, free electron alone, whose energy is related to the Fermi level, is involved in case of photoelectric effect. The current produced in photoconductivity is directly related to the incident light intensity, and this phenomena is utilized in photographic light meters. Cadmium sulfide is commonly used for the detection of visible light, as in light meters, and solar cells are also one of the application which is based on photoconductivity. Other applications of optical properties is lasers. So laser is an acronym for light amplification by simulated emission of radiation, and unlike luminescence, which produces incoherent light, the light produced by laser emission is coherent, and it is constant phase difference and a same frequency will be here. This is based on the fact that in certain materials, electrons excited by a stimulus produce photons, which in turn excite additional photons of identical wavelength. Example, the materials which show this phenomena, laser, these are ruby, which is a single crystal of alumina which is doped with the little amount of chromium oxide, which gives it its color. Yttrium, aluminium garnet, known as YHE, Y3Al5O12, it is doped with neodymium, Nd, and helium neon laser, and some semiconductors like gallium arsenide and indium gallium arsenic phosphide. Applications of lasers, so these are in welding, metal cutting, heat treatment, and in performing some surgeries, as for example eye surgeries, reading compact discs, etc. Other application is optical fibers. So these are the medium for carrying information from one point to another in the form of light, and fiber optics is not electrical in nature, unlike the copper form of transmission. So when we use copper wires, that type of transmission takes electrical signal from one point to another. So electron will have to transfer from one side of the wire to the other side of wire. Electrons will be involved in that case. And in this case, It has been calculated that it would require 30,000 kg of copper to transmit the same amount of information as only 0.1 kg of optical fiber material. So this is very fast type of information transfer because it involves light, and speed of light is very faster compared to speed of electrons that will be inside your copper wire. Now the information, for example, telephone conversation in electronic form is first digitized into bits, and that is ones and zeros. Then it is accomplished in the encoder. Then electrical signal is converted into an optical photonic one using the electrical to optical converter, which is normally a semiconductor laser. Then this laser emits monochromatic and coherent light, infrared region, low absorption losses. So the output, this light, pulses of light, it will be transferring from one end to another end. So a binary 1 and a 0 type of pulses will be there. So the pulse signal are then fed into and carried through the fiber optical cable, and at receiving end reverse process takes place. So we'll be converting this light signal into again this type of firstly we'll be converting it into codes, then we'll be converting it into telephone conversation. Now this is what your this, as I told, this whole process, it is here shown easily. So firstly it is encoded your conversation, then it is converted into electrical or optical converter using this. Then this is the fiber optic cable. So this is sent through this optical signal. Repeaters are in between, so it will be coming here. Then we'll be converting this optical signal into some readable signal. Then we'll be decoding it, and this will be your output signal. And this is the your structure of optical fiber. These are the components. So first is core, which is the innermost part. It passes signal through the core, and cladding, this is the cladding which constrains the light rays to travel within the core. So by having different type of refractive indexes, we can restrict our light inside just this core area. So it will be keep on internally reflecting. So final one is a coating which protects core and cladding from any damage. So this is the size ranges. So inside core will be 8 to 62 micrometer, cladding is 125 micrometer, and this is up to 900 micrometer. So it is less than your in millimeter. So this size is very small, very compact. Now this is what your optical fiber it looks like. Now the applications of optical fiber. So this fiber it experiences geometrical, size, shape and optical changes. So these, depending on this, the nature and the magnitude of perturbation. So with change in, if there is change in, for example, refractive index because of any stress or any other type of parameters, so this can be converted and read through, and this can be used as sensors. So the optical fiber serves as a transducer, and it converts measurements like temperature, stress, strain, rotation or electric and magnetic currents into a corresponding change in the optical radiation. And since light is characterized by intensity, phase, frequency and polarization, any one or more of these parameters may undergo change. So there are two type of sensors. First is intrinsic. So this is intrinsic. So here your optical fiber itself will act as transducer. So this will be, so here parameter is changing, it is itself detecting it, and modulated light is getting out. Extrinsic will be, it will use fiber to supply light to a sensing device. So this device will sense any change in temperature or anything, and it will send different signal to the optical fiber. Now moving on to from optical to thermal properties. So thermal properties, they describe the response of a material to the application of heat. So as the solid absorbs energy in the form of heat, its temperature rises and its dimensions increases. And so there will be some expansion when we heat some materials, and it is important. Some important thermal properties are heat capacity, thermal expansion, and thermal conductivity. And polymers, they have significantly larger Cp, which is heat capacity, because covalent bonds in polymers do not let atoms exchange electrons as metallic bonds do. Now these are various materials and their heat capacities. For example, for polymers, polypropylene, polyethylene, polystyrene, Teflon, these all have these heat capacities at room temperatures, which are higher compared to ceramics and metals. Then below these there are ceramics, and lowest are of metals. So ceramics are magnesia, alumina, glass, they have 900 to 800, and in case of metals we have around 100 to 900. We have wide range from aluminium, steel, tungsten, gold. Now heat capacity, it represents the amount of energy that is required to produce a unit temperature rise, and it is indicative of a material's ability to absorb heat from the external surrounding. So this can be written as energy change, gain or loss, divided by resulting temperature change. So dQ upon dt. Heat capacity increases with temperature. So as we are increasing temperature, your heat capacity will keep on increasing and will attain a maximum limit. Now it increases with temperature, and for solids it reaches a limiting value of 3R. R is your gas constant. Now from an atomic perspective, energy is stored as atomic vibrations, and as temperature increases, the average energy of atomic vibrations increases. So as we are increasing temperature, vibrations are increasing, so this heat capacity is also increasing. Thermal expansion. So this is another property. Now temperature of a solid is a measure of its potential energy, and most solid materials expand upon heating and contract on cooling. So as this potential curve we see at particular at the bond length, it will be having certain length. So this length, if it keep on increasing temperature, so it will be expanding. Now heating to successively higher temperature rises the vibrational energy. Thus the interatomic separation between from R0 to R1, R2, R3, R4, R5, like this it will keep on increasing. The greater the atomic bonding energy, the deeper and narrower this potential energy trough will be. Thus the increase in the interatomic separation with a given rise in temperature will be lower. Now for materials, in case of metals, it is 5 to 25 times 10 to the power minus 6. These are the expansion values. So expansion is lower in case of ceramics, which is 0.5 to 15, and it is very higher for polymers because polymers expand a lot, which is from 50 to 400. Now another property is thermal conductivity, and thermal conductivity is the phenomena by which heat is transported from high to low temperature regions of a substance. Now Fourier law states that for a steady state, the heat flux is directly proportional to a temperature gradient. Now Q upon A is your temperature, your heat flux, and this is equal to minus K times dK upon dx. dt upon dx is your temperature gradient. So with change in your like along particular let me use pointer. So if this is your metal rod, so along the x will, with changing in distance, you measure your temperature, that will be your temperature gradient. So this will be proportional to your heat flux, and there will be a proportionality constant which will be K, and K will be your thermal conductivity of that material, which is measured in watts per meter Kelvin. And their minus sign is because this heat will be flowing in the direction of decreasing temperature. So from high temperature to lower temperature, it will be moving in that direction. Thermal conduction in a solid takes place by both lattice vibration waves known as phonons and free electrons. Thus total conductivity is addition of both of these. So lattice vibration is KL, and because of electron, your thermal conductivity is KE. Now thermal conductivity for metals. So metals are extremely good conductors of heat because they have relatively large number of free electrons that participate in thermal conduction. The purest form of metal will have highest thermal conductivity than the alloy form. So as we keep on increasing amount of some alloying elements or impurities, this heat conductivity will reduce. In the alloy, different atoms will have different electron affinity, thus movement of the excited electrons becomes hard. And since free electrons are responsible for both thermal and electrical conduction in pure metals, the two conductivities are related by Widman-Fren's law, and this law states L equal to K upon this sigma T. L is Lorentz constant, K is thermal conductivity, sigma is electrical conductivity, T is absolute temperature. Now these two are related because both of these will be depending on free electrons that are present. Now for materials, silver, copper, gold, aluminium, iron, steel, these are the thermal conductivities. Silver has highest 410, copper has little bit lower than it 385, and gold has 340, aluminium has 210, iron has 80, and steel has 52. Now for ceramics, they are thermally insulator as they lack large number of free electrons. In this case, your heat will be conducting through the presence of phonons. So thus the phonons are primarily responsible for thermal conduction. So Ke will be lesser than Kl. L is your lattice vibrations. Also, the phonons are not as effective as free electrons in the transport of heat energy due to the phonon scattering, because there will be some lattice imperfections. So if there are, for example, some vacancies present or some dislocations present, they will be scattering this thermal conductivity. So these phonons will be scattered and the heat won't be efficiently going through one part to another part. The room temperature thermal conductivities range between approximately 2 to 50 watts per meter Kelvin, and amorphous ceramic have lower conductivities than crystalline ceramics as the atomic structure is highly disordered and irregular. Now higher porosity also reduce the conductivity due to the presence of still air. So the air will be trapped inside those pores or certain gases will be there. So these will be having very low conductivity. So it will reducing your entire conductivity of material. Now for polymers, thermal conductivities for most polymers are of the order of 0.3 watt per meter Kelvin, which is very lower. So the handles of cookers and all those are made using polymers. Now energy transfer is accomplished by the vibration and rotation of the chain molecules. So it has entirely different method of this heat transfer. Now magnitude of the thermal conductivity, it depends on the degree of crystallinity. Highly crystalline and ordered structures, they means effectively coordinated vibration and higher thermal conductivity. Now these are the materials and their thermal conductivities and the energy transfer mechanisms. Now in case of metals, aluminium, steel, tungsten, gold, they have very high thermal conductivities and it occurs due to atomic vibrations and motion of free electrons. In case of ceramics such as magnesia, alumina, soda lime glass, silica, these all have very low thermal conductivity and it occurs due to atomic vibrations. In case of polymers, polypropylene, polyethylene, polystyrene, Teflon, these have lowest of the thermal conductivity among these and it occurs due to some vibrations and rotation of chain molecules. Now thermal stresses and shock. So thermal stresses are stresses induced in a body when due to changes in the temperature the deformation is hindered, and thermal stresses in a constrained body will be compressive nature if it is heated and vice versa. So if we kept for example we kept a metal inside restricted under certain constraints, so when we are trying to heat it, so the walls will be putting some compressive force on it, so there will be compressive nature type of stresses inside this material. Thermal shock. So if the dimensional changes in a material are not uniform, for example if I am heating a metal from only one side, then there will be some temperature gradient inside that. So along one part where it is heated, there will be some expansion in material and other side will be as it is. So it will be having some thermal shock. So this may lead to fracture of a brittle materials like ceramics and it is known as thermal shock. So the capacity of a material to withstand thermal shock is defined as thermal shock resistance and as TSR, and it is given as sigma F times K divided by E alpha 1. So for the high thermal shock resistance, so here alpha F, sigma F is your fracture strength, K is your thermal conductivity, E is elastic modulus, alpha is thermal expansion. So if we want very high thermal shock resistance so that material doesn't fail because of this, then we will be requiring lower values of these two, which is elastic modulus and expansion coefficient. So we'll be requiring lower values of elastic modulus and alpha 1 thermal expansion coefficient. So your material should not expand much on heating. It should have low elastic modulus, because if it has high elastic modulus, it will be very stiff, so it will be more likely to crack. And if it should have very high values of thermal conductivity K and fracture strength. Now other properties are electrical properties, and very important equation is your Ohm's law, which is voltage is proportional to your current, and there will be proportionality constant, which is resistance. So V is voltage drop in volts, I is current in ampere, R is resistance of material in ohms. Now material's electric resistance is an extrinsic property and it depends on object geometry. Now for removing this dependency, we take resistivity, another constant which is independent of specimen geometry. So it is intrinsic property, but it is related to R through the expression R equals to rho times L upon A. So L will be your distance between voltage measuring points. For example, this point and this point, and cross sectional area perpendicular to the direction of current flowing. So the unit will be unit of your this resistivity will be ohm meter. This is your electrical circuit. So this is your variable resistor. This is your current measurement ammeter. This is voltmeter. This is cross sectional area. This is length. Your specimen for which you are measuring your resistance. This is your battery which is supplying this current. Now the electrical conductivity is another property. So electrical conductivity is indicative of the ease with which a material is capable of conducting an electric current. Now electrical conductivity is simply inverse of resistivity. So unit will also be inverse. So ohm meter inverse will be its unit. On the basis of conductivity, solid materials can be classified as conductors, semiconductors and insulators. In case of conductors, your conductivity will be higher than 10 to the power 7 ohm meter inverse. For semiconductors, it will be between 10 to the power minus 6 to 10 to the power 4. And for insulators, it will be lesser than 10 to the power minus 10 ohm meter inverse. And this conduction can be of two types. It can be electronic and ionic conduction. Electronic conduction will be arising due to current arising from the flow of electrons. And ionic conduction is current arising from net motion of charged ions. So it will be mainly inside electrolytes. Now these are the metals and their electrical conductivities. Silver has the highest 6.8, then copper has little bit lower 6, and lower is gold, aluminium, brass, iron, platinum, plain carbon steel, stainless steels. Then in case of graphite, it has 3 times 10 to the power 4 to the 10 to the power 5. which is very closer to the metals. And other ceramics, they are insulators. So these will be having from 10 to the power minus 9 to up to 10 to the power minus 18. In case of polymers also, they also have very low conductivity. Now, effect of temperature on metal conductivity. Now, increasing temperature causes greater electron scattering due to increased thermal vibrations of atoms. Hence, the resistivity of metal increases or conductivity decreases linearly with temperature, and the total resistivity of a metal is the sum of the contributions from thermal vibrations, which is rho T. Impurity is rho I, and plastic deformation because of rho T. So because of these, different types of resistivity will be arising because of vibrations, because of presence of impurities, because of this deformation, which will be generating crystal defects, mainly dislocations. Now, scattering mechanisms act independently of the one another. Now, in case of insulators, they have very wide band gap, greater than 2 electron volt, and very few electrons get excited across band gap. For semiconductors, this gap will be lesser than 2 electron volt, and more electrons they get excited across band gap. Now on the x-axis we have temperature, on y-axis we have electrical resistivity. So as we keep on increasing temperature, electrical resistivity increases for metals. So for pure copper, we can see it has the highest conductivity, so it is here. Then if we add some very less nickel in it, then we see its resistivity increases, and we keep on increasing nickel, this resistivity keep on increasing, and with temperature as well, this keep on increasing. Now moving on to finer properties, which are magnetic properties. So the magnetic field is a force which is generated due to energy change in volume of space, and a magnetic field is produced by an electric charge in motion. For example, current flowing in a conductor, or simply an orbital movement of and spin of electrons. So it can be orbital movement, so this electron can be in orbit, or it can spin on itself when it spins. These both causes some magnetic moment. Now origin of magnetic moments. First is orbital motion around the nucleus. Now electron is considered to be a small current loop which generates a very small magnetic field having a magnetic moment along its axis of rotation. Spin of electrons. The spin of electrons are also produces a magnetic moment along the spin axis, and spin magnetic moments can be only parallel or anti-parallel. Now there are mainly 5 types of materials in terms of magnetic properties. First are diamagnetic materials, and its property is diamagnetism. So this is a weak form of magnetism which arises only when an external field is applied. So it arises due to a change in the orbital motion of electrons on the application of a magnetic field, and there are no magnetic dipoles in the absence of magnetic field, which is shown here. When there is magnetic field is 0, then there are no magnetic moments, and when we applied magnetic field in this direction, then these moments they are aligned in opposite field direction. And the magnetic susceptibility, which is a ratio of magnetization and field intensity, is negative, and B in diamagnetic material is less than that of vacuum and is repelled by the applied magnetic field. Now, these are examples of some diamagnetic materials: alumina, copper, gold, silicon, and zinc. Other materials are paramagnetic materials. In this, the cancellation of a magnetic moments between electron pairs is incomplete. Hence, there will be some magnetic moments exist without any external magnetic field. So, when we have no external field, then also there will be some moments. However, the magnetic moments are randomly aligned, hence no net magnetization without any external field. When a magnetic field is applied, all the dipole moments are aligned in the direction of the field and the magnetic susceptibility is small but positive. So here value of B in a paramagnetic material is slightly greater than that of vacuum. Paramagnetic materials are aluminium, chromium, molybdenum, titanium, zirconium. Other materials are ferromagnetic materials. Certain materials possess permanent magnetic moments in the absence of an external magnetic field, and this is known as ferromagnetism. Permanent magnetic moments arise due to the uncancelled electron spins by virtue of their electron structure. A coupling interactions of electron spins of adjacent atoms, they cause alignment of moments with one another, and the origin of this coupling is attributed to the electron structure. So for example, in D block elements, when they have electrons which are not coupled, for example in case of iron, we have 26 its atomic number and 4s2 3d6. So 4 of the electrons are not coupled, and so it have incompletely filled d orbitals and hence unpaired electron spins. So it shows permanent magnetism. Antiferromagnetism. If the coupling of electron spins results in an anti-parallel alignment, then spins will cancel each other and no net magnetic moment will arise. This is known as antiferromagnetism. Manganese oxide is one such example. In manganese oxide, O2 minus ions have no net magnetic moment and the spin moments of Mn2 plus ions are aligned anti-parallel to each other in adjacent atoms. Ferrimagnetism. In this, certain ionic solids having a general formula MFe2O4, where M is an any metal, show permanent magnetism, termed ferrimagnetism, due to the partial cancellation of spin moments. In Fe3O4, Fe atoms can exist in both 2 plus and 3 plus states as Fe2 plus O2 minus and Fe3 plus to O2 minus 3 in a 1:2 ratio. The anti-parallel coupling between Fe3 plus moments, they cancel each other, and Fe2 plus moments are aligned in the same direction and result in a net magnetic moment. Now in case of Fe3 plus cation, this is complete cancellation will be there. In Fe2 plus there will be some magnetic moments. Now effect of temperature on magnetic behavior. So the atomic vibration increases with increasing temperature, and it leads to the misalignment of magnetic moments as they are free to rotate. So these are the magnetic moments. These are domains. So as they are free to rotate above a certain temperature, all the moments are misaligned here as it is shown, and the magnetism is lost. This temperature is known as Curie temperature. Tc is its symbol. Now the magnitude of Curie temperature varies from material to material. So for example, if we want to find out service temperature of certain material, so we can use, if we are using cobalt as a magnet, then this is the highest temperature we can use it. For iron it is 768 degrees C. For cobalt it is the highest 1120 degrees C. For nickel it is 335 degrees C. For Fe3O4 it is 585 degrees C. Now ferromagnetic materials exhibit small volume regions in which magnetic moments are aligned in the same direction. These regions are called domains, which are shown here. These are the domains and these are the domain boundaries or domain walls. Now adjacent domains are separated by domain boundaries. The direction of magnetization changes across the boundaries. For example, magnetization is in this direction. For it is in this direction. The magnitude of magnetization in the material is the vector sum of magnetization of all the domains. Now below Tc, this is what material look like. It will get magnetized in various directions depending on domain, and above Tc there is not these magnetic moments, they are free to rotate. Now with increasing temperature, saturation magnetization is coming to 0. Now depending on the properties, there are soft and hard magnets. Now energy product, kilojoule per meter cube. So area of the largest BH rectangle that can be constructed within the second quadrant of the hysteresis curve. So this is your hysteresis curve, this is your first quadrant, this is your second quadrant, third and fourth. So in this second quadrant, when you make the largest possible rectangle, so the area of the largest BH rectangle which can be constructed within the second quadrant of the hysteresis curve. So for various materials, this loop will be different, like for some it will be like this, for others it will be like red one. So depending on that, they will be having energy product. Now it represents energy required to demagnetize a permanent magnet. So large BH max, it will be harder is the material in terms of its magnetic characteristics. Now depending on that, for soft magnets, they will be having narrow hysteresis curve. Now this is for soft magnets, this bigger one is the for hard magnets. Now hard magnets have broad hysteresis curve, high initial permeability and low coercivity, which is easy movement of domain walls. For hard magnets, low initial permeability and high hysteresis, energy losses and high coercivity. For soft magnets, these are easy to magnetize and demagnetize. Hard magnets are difficult to demagnetize. Examples are iron silicon alloys, nickel iron alloy and iron. These are used widely in generators, transformers and switching circuits. For hard magnets, Alnico, which is an alloy of aluminium, nickel, cobalt and iron, and ferrites, rare earth cobalt, ceramics, rare earth, cobalt, cobalt platinum. These alloys, they are hard magnets. Now hard magnets are used in all permanent magnets in applications such as power drills, motors, speakers, etc. Now this is your BH curve. So when you start magnetizing your material, then you try to demagnetize, and this is what your curve looks like. So this point on the y-axis, this, it is your remanence. So it is a measure of the remaining magnetization when a driving field is dropped to zero. This is your coercivity, which is a measure of the reverse field needed to drive the magnetization to zero after being saturated. So after saturation, all the domains will be aligning them in the direction of the applied field. Now in opposite direction, and in this direction also you will be finding saturation, then again you will be finding remanence, then here coercivity, like this. So this is your B. Here you will be finding a rectangle having highest area, that will be your pH product. Depending on that, you will be deciding whether it is a soft magnet or a hard magnet. Now this is all. Now if you have any query, you can ask. This was your first question. Which one of the following properties do not belong to diamagnetic properties? So we know that its magnetic susceptibility is negative, which is lesser than vacuum. The second question was the ratio of intensity of magnetization to the magnetization force is known as. Answer will be susceptibility. Third question was which of the following is expected to have maximum permeability? Answer will be ebonite, because others are diamagnetic materials, and this is paramagnetic. Which of the following materials is considered as a non-magnetic material?
Madam, third
Yes.
question, what reason? Once again, madam.
Yes.
Third question, reason. Answer reason.
Yeah. So brass, copper, zinc, these all are your diamagnetic materials. Their susceptibility is lesser than zero, like we saw here. And permeability wise, the magnetic permeability of material is its ability to acquire magnetism. So when we will be applying magnetic field, they'll be aligning themselves in opposite direction. And compared to ebonite is paramagnetic. It has highest permeability among these options. Okay.
Magnetic property must be magnetic susceptibility must be high.
Magnetic susceptibility will be also be higher for paramagnetic. It will be positive compared to, like, it will be negative for diamagnetic one and positive for paramagnetic materials. Susceptibility is just the ratio of when you are applying this field intensity and your material is getting magnetized.
Okay, madam.
Okay, fourth question is which of the following is considered a non-magnetic material? Now we know that diamagnetic materials, they have susceptibility lesser than 0, negative, which is lesser than vacuum. So these are known as your non-magnetic materials. Fifth question is for transmitting the electrical energy over a long distance, the general preferred material is. Options are copper, steel reinforced aluminium, aluminium reinforced copper, or aluminium reinforced silver wire. So your answer will be steel reinforced aluminium. So ACSR is used, which is aluminium core steel reinforced. Sixth question is a material has refractive index of 2.5. If the light is falling normal from the glass sheet of refractive index 1.5, what will be the approximate reflectivity of the material? So this formula we used. R is reflectivity and N1 and N2 are the refractive indexes. So N2 minus N1, N2 plus N1 times square. So this will be 0.0625. Question 7 is in order to increase the electrical conductivity of a metal, the preferred method is increase the vibration level, decrease the temperature, increase the temperature, or decrease the vibration level. So we know for metals with increasing temperature, resistivity increases. So for increasing conductivity, we will have to decrease temperature. Eighth question is which effect is not related to light absorption mechanism? And these are the options: Tyndall effect, Compton effect, photoelectric effect, or Peltier effect. Peltier effect is dependent on your current and temperature difference. So this will be your answer. Others are dependent on light absorption. Ninth question is light travels from air into an optical fiber with an index of refraction with 1.44, and in which direction does the light bend if the angle of incidence on the fiber is 22 degree? What is the angle of refraction inside the fiber? Options are it bends towards normal in 15 degree or 25 degree, or it bends away from 15 degree and 25 degree. So we have to just use Snell's law. So refractive index of air, you know that it's 1.003 and the angle with air is 22, then N2 will be 1.44 and theta 2 you have to measure. So simply you can get it will be 15.08, and by using this you can say that it will be bending towards the normal and at 50 degree. 10th question is the highest value of thermal conductivity is expected for. So we know that for solids it is highest. So for solid ice it will be having presence of phonons as well. So this will be showing highest thermal conductivity. Now these are the lecture slides. I will be just these are the applications of optical properties: luminescence, photoconductivity, lasers, optical fibers, then their components, applications, then thermal properties, heat capacity, thermal expansion, and thermal conductivity. Then we saw it for metals, ceramics, and for polymers. Then we read about thermal stresses and thermal shock. Then electrical properties, electrical conductivity, effect of temperature on metal conductivity. Then for magnetic properties, it arises because of these magnetic moment, because of electron rotation and their spin. Diamagnetism, these are the types of magnetic materials. They can be diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetism. Then we saw temperature influence on magnetic behavior. So there will be a Curie temperature above which it will turn into paramagnetic. Soft and hard magnets. So these are the differences. Then we saw the BH curves.
Why that we'll take only second quadrant when we are getting from rectangle?
So because we want to know how easily we can demagnetize our magnet. So in this case, this quadrant, you are trying to magnetize it. You are applying this field and it is trying to get magnetized. When then we try to from 1 second, let me use pointer. From here you are trying to go in opposite direction so that it demagnetizes. You are applying this your field in opposite direction. So when you'll be,
Why not?
yeah,
Why not third? Why not third? Third is also demagnetized.
in third we are trying to demagnetize it again. In third we are going in this direction, so it is magnetizing in opposite direction. In this
That
quadrant we are trying to demagnetize it. So we are trying to find how easily we can demagnetize our magnet. So that's why
in
you,
third also it will be magnetized again.
it is getting magnetized in opposite direction. We are
Opposite
achieving
direction.
saturation. In this quadrant you will be demagnetizing it.
Only in second it is demagnetized.
Yeah, here you will be taking a rectangle with highest area.
Thank you. Do you get that older lecture videos?
Older Excel.
That is week 1, 2, 3, 4 like.
Yeah. Do you have the Google Drive link with you?
Yeah, I have.
Okay, so there you have all the 1 to 7 you have, and 8th I'll upload today.
Okay. 1 to 7 we have only PPTs.
Yeah, PPTs are there. Lecture slides.
Yeah, lecture slides we have, but recording of this lecture.
Recording of lecture you can find on YouTube.
Okay, YouTube.
From NPTEL they must have shared links to that, I think.
I'm asking this without clarification. Right.
It doubt these YouTube, yeah, YouTube links also they must have shared links with you. You can easily search on YouTube doubt clearing sessions for this particular nature and properties. I think you'll find this.
Just I have typed one question related to survival probability of CPS alumina.
Hmm.
Uh, what I I don't know how to solve that question. Can you please?
In which lecture?
This is in third lecture.
Survival probability. I haven't seen it either. Sir asked this question.
Sir has not asked. I have seen in the related content. I have seen like
Sir, did sir give you formula for survival probability?
I don't know the survival probability formula.
Did
That's
sir
all.
teach you this concept, survivor probability?
Other teaching assistants are has given this type of problem, madam. I didn't attend that. That's why.
Okay. Because I don't remember going through such lecture slides, I don't remember going through this concept. So if it is not there, then I don't think they will be asking question in exam based on that. But if other TA covered it, then you can go through their lecture slides.
Regarding Miller indices, this is
Yes.
also one question. What are the Miller indices of the direction that intersects the x, y, and z axis at 2, 3, and 6 units respectively? That
Basi-
question also I have not understood.
You have to find Miller indices of plane.
Miller indices of the direction that intersects the x, y, and z axes at 2, 3, and 6 units respectively. Like that question has been.
Should be a plane, only plane can intersect at three different points. How can a direction intersect at 3 points? Where did you find this question?
Maybe plane. For
Yeah.
that, he is asking to find out the direction, I think.
So you have to take reciprocals of these, right? Multiplied by. It will be 3 to 1. 3 to 1 plane, right?
2,
3
2,
to
3, 2, 3, and 6 units he has given.
2, 3.
6.
How can it be 2, 3, 6? It will be 3 to 1. Your crossing points were 2, 3, 6, right?
Yes, madam. X axis 2, y axis 3, z axis 6 units.
2, 3, 6. Then you will be taking reciprocals 1 by 2, 1 by 3, 1 by 6. Then you will be reducing these, so you will be multiplying these with 6. So so it will be 3, 2, 1. It will be 3 to 1 plane.
1 by 2, 1 by 3, 1 by 6.
Yeah, then you'll be reducing these. So for that you'll be multiplying it with 6.
This 3 to 1 represents what, madam?
Your plane or the direction that is normal to this. These are Miller indices of plane.
Based on the Miller indices only, one more question. Which of the Miller indices are perpendicular to 1, -1, 0 for a cubic system?
1
Options are
1 0
op-
minus 1.
1, -1, 0, madam.
1 minus 1 0. Yes. Options are
Options are 4, 4, 0. Another option 0, 1, 0. Another option 3, 0, 0. Another option -2, 2, 2. He is asking Miller indices are perpendicular to 1, -1, 0 for a cubic system.
okay. So answer will be 440.
Answer he has given 0, 1, 0. He has given answer.
Your initial was 1 minus 1 0, right?
1, -1, 0, madam.
So their dot product should be 0 for perpendicular. So it will be 0 for only 440.
What is the condition, madam? What is the condition?
Their dot product should be 0.
Dot products, how to cross check, madam? The options and the values we have to cross check.
Your option, can you repeat your, firstly it is 1 minus 1 0, right? For
1
which we
minus
have to find.
1, -1, 0, madam. He has given.
Then options are 440,
On, madam.
010,
Yes, madam.
300,
Yes, madam.
minus 2, 2, 2.
2, 2. -2, 2, 2.
Okay. So for only 440 it is giving dot product 0. I think answer should be 440 according to me.
How to solve, madam, that question?
For perpendicular, you have to like keep your dot product 0. So for dot product, yeah, you'll be like multiplying h1 h2 plus k1 k2 plus hkl l1 l2. So this all addition should be 0
H1 H2 plus K1 K2 plus
plus L1 L2.
L2 must be 0, no, madam?
Yeah. So it will be 0 for only 440. Let me confirm once. These were two directions, right?
Question has given which of the Miller indices are perpendicular to 1 minus 1 0 for a cubic system. Like that, I has given question. Options are given as I have said just now.
Okay.
One more question on the planar density of a cubic unit cell in an FCC crystal. Calculate the planar density of a cubic unit cell in an FCC crystal manner. Yes, given. Options are 2 by a square, 33 by a square, 44 by a square, uh, 2 by a square. Like that he has asked. Options are given.
First,
Planar density of a cubic unit cell in an FCC crystal.
first one was 2 by a square.
Yes, madam.
Last one also you said 2 by a square.
And last one he has given root 2 into root 2 divided by a square he has given.
Root 2 into 2. Okay, for FCC, planar density.
Planar density means total area.
Total area is a square. Area of atom that is covering that particular plane divided by area of plane.
Planar density means total area of all the atoms in the unit cell that are
No,
exposed to the surface and then surface area of the unit cell.
yeah, whichever plane that you are taking, for that particular plane it will be having certain density of atoms. So atom is covering certain area, so that area you have to take, divide by entire area of that plane.
So in this case, FCC crystal means uh, total area of all the atoms in the unit cell are
Not total area
total.
on that particular plane. So it can be plane, whichever plane you are taking. So if it is face, plane on face, then face has an atom at the center, then also on corners. So you have to count that area, then divide by entire area a square. That's how you can calculate.
Once again, please repeat, madam.
Okay, should I okay, for consider, one second, let me use the presentation for example. So consider this square is there, right? This square is there on presentation.
Question is planar density of a
This
cubic
on the
unit cell.
screen, yeah, on the screen you are seeing this square, right?
Ah, yes, madam.
So this is, for example, this is a plane on your FCC. So FCC has a lot of planes. You can consider one plane. So this entire plane, it will be a square. Its area is already a square. But these, for example, these atoms are covering this area. So this area of these atoms, cross section area. So this area divided by entire area of this plane. Then that will be your planar density.
Okay. Definition I have understood now. In this question, he is asking planar density of a cubic unit cell in an FCC crystal. He is asking
Cubic unit cell in FCC.
crystal. In FCC crystal, why he is asking cubic unit cell? I don't understand.
No, in cubic only you have FCC, right? In case of cubic, then you will be having this. Uh, Cubic will be means there will be a, all lattice parameters are equal, a alpha a equal to b equal to c. So
Yes,
for
madam.
in that case you will be having face centered cubic. So for face centered cubic it is trying to get planar density. So for that it should like tell on which plane you have to calculate. Like for example, along 100 plane for simple cubic, it is shown planar density will be 1 upon a square. So for a particular plane you can calculate.
So in this case, the option may be 2 by a square, madam.
2 by a square.
2 upon a square.
By
4 upon a square.
for different planes it is given different. For FCC it will be 2 upon a square. What are the options? 2 upon a square is there, right?
2 upon a square, first
So,
option, madam.
so for 100 plane, it will be 2 upon a square. For 110 plane, it will be different, like root 2 upon a square. And for 11 plane, it will be different. It will be 4 upon root 3 a square. So you have only one option that is common. So it is 2 upon a square.
So the question must be uh, framed as you have said, like that plane he has to
Yeah, it
mention,
should.
madam.
Yeah, it should tell which along which plane also, because planar density will be different at different planes.
Oh. Mhm. One more question. What is the primary slip
Slip
system
system. Yeah.
of a BCC crystal?
For BCC. Okay, for
BCC crystal. What is the primary slip system of a BCC crystal?
okay, it should be 111 and 110. So 111 will be your direction. 11 direction and 110 plane. What are the options?
Uh, as you have said, the option has given that option has given, madam. Your
Okay.
as you
So,
said just now, the option has given.
yeah, for example, like you can think it in this way, like if you have BCC crystal structure, then at the body center of the unit, you'll be having an atom. So your direction will be when 111, it will be along your diagonal, body diagonal. So along body diagonal, you have highest packing density. So that's why 111 direction will be there and plane will be 110. Okay, that's how you can remember it.
Slip system means, madam. Slip system meaning.
Slip system meaning it will be like combination of direction and plane. So it along this direction and plane, it will be having highest atomic packing density. So it is easily packed, so it will move easily when you will be applying some force on it. So it will try to move along this direction and this plane.
Okay, okay. Thank you, madam.
Okay.
Highest along this direction, highest packing
Packing
factor. No?
density. Yes.
Any numerical based questions, if you have, please explain, madam.
In this presentation, I only had two numericals.
Before that also, as it is the last lecture,
Yeah.
uh, whatever you feel it will be useful for the examination, you can please summarize, madam.
Okay, the numericals.
Next week we are having an exam, madam.
Okay. So, in composites, I didn't have. In polymers, I had questions.
Regarding Miller indices, if you have any problems, please tell,
In
madam.
Miller indices, I don't think I included questions.
Numerical
Okay,
problem in Miller
I'll
indices.
start second. Okay.
I have some doubt regarding Miller indices.
Okay, let me share the presentation. Yeah, okay. It's visible, right?
Yes, madam.
So, where I have told regarding these Miller indices. I'll go through them. Then, yeah, okay. How to calculate Miller indices. So, in case of like plane is there, if you have to find out plane, it is visible, right?
Yes, madam.
So if this plane is there, so if these are the points it is crossing C, A, B, then you have to firstly find its reciprocals. So you have to do 1 by A, 1 by B, 1 by C. Okay? Along
Yes.
x direction, you have to take 1 by A, y direction 1 by B, C direction 1 by C. Then these will be your indices. Now you have to reduce them. For reducing, you have to either multiply it with something or you have to divide. If it is, then for example, here it is crossing it at 1 1 1. Okay, then
Yes, madam.
reciprocal will also be 1 1 1. So if it was 2 to 2, then you could have divided it with 2. Or if it would be 0.5, something like that, then you could have multiplied it with some numbers so that these all will become integers. So you have to bring them to integers, then you have to put it in this bracket, small bracket. It will be plane. In case of plane, you have to take reciprocals. So remember it like that. In case of direction, you have to just follow how you are getting to end point. For example, you are starting here, so how much you are moving in x direction. So however you are moving, you have to put it in x part. Okay, for example, you are moving in positive direction for 1, right? Here you are moving one step. Here you are moving one step in opposite direction for y. So opposite negative you have to put 1 bar. And if for z you are moving in positive direction 1 times. So you have to put 1. So it will be 1 bar 1. In similarly you have to make it integer. As I told earlier, you have to either multiply it with something or you have to reduce it to bring it to integer. So
Based
that,
on based on this concept, Miller indices of a direction,
yes.
the, how the question will be, how the numerical question will be framed, madam, based on this Miller indices of direction.
So for
Question will
example, they can ask you which they can show you certain like cross that a plane is crossing it at these points. So you have to take its reciprocal and show it in plane terms. You can have examples like that. Or for example, as you told me earlier, like they can ask which line will be perpendicular to it, which direction will be perpendicular. So you can use dot product and find out which will be 0. So that too will be perpendicular. Or in case of direction, they can show you direction. It will be objective questions, right?
yes, yes. Objective question will be how the objective question will be framed based on this
So
concept.
in direction, they will be showing you direction. They can't ask you how to draw direction, so they can show you direction and then ask which direction is this. And for direction, you have to remember there will be square brackets always. So this is how you have to draw. So if you know how to draw a direction, so you can easily identify which direction is this. Okay. So initially I have questions, so I'll check whether there are some related to Miller indices. So sir asked one questions like a family of Miller direction is always represented as. So in this you have to remember like how to denote a family of direction, how to denote a single direction, how to denote plane, family of planes, how to denote a plane. So these four you should remember at least if a question like this comes. And these are the packing effective number of atoms. This is easier. You can easily calculate. For example, corner atoms in simple cubic. In BCC you have to add one body center atom also. In FCC you have to add face center atoms.
Yes, yes, ma'am.
Coordination numbers are also you should remember. Slip is there. Defects, type of defects. Okay. Okay, packing efficiency I told, packing fraction. So these are volume, for volume. So you had to use volume in this case. So for example, you asked me planar density,
Hence,
right? So
yes,
in
yes,
this case, this plane is there, for example. Okay.
yes, madam.
So this face plane is denoted as 100 plane, right?
Yes, madam.
So for example, this plane will have different planar density, and if there is a plane 110 which will be diagonally in this, so that plane will have different type of packing density. So that's why you'll be having different densities along different planes. So
He
like
has asked in that question cubic, cubic,
cubic
what?
meant that these lattice parameters will be equal. So example, this cubic system in which A, B, C, these all are equal, right? So all your systems BCC, FCC and simple cubic, these three are based on this cubic system. So these all will be having these lattice parameters equal. That's what that part meant.
In that question, he has asked calculate the planar density of a cubic unit cell in an FCC crystal.
Yeah, for FCC, they should have mentioned plane, but other options are not for FCC, so you can just guess like 2 by a square is for one of the planes, so you can get 2 by a square, okay?
Okay, okay, madam. Very helpful, madam. These lectures are helped a lot.
Okay, thank you.
Are you going to end this session, madam?
Yes, it's 5 o'clock. You have any
Okay.
query?
Uh, no, madam. Thank you. Thank you very
Okay,
much, madam.
okay,
Helped a very. Okay,
okay.
madam.
Best of luck for exam.
Okay, okay. Thank you, madam.
Okay.
Presentation